Look at medieval peasants and see primitive poverty. We imagine coarse, tasteless food barely fit for survival. But their daily bread, the foundation of their existence, was something entirely different. It was a biological masterpiece that outperformed anything you'll find in a modern supermarket. One thick slice of their sourdough delivered more usable nutrition, more sustained energy, and more digestive benefits than 5 slices of today's processed white bread. And it achieved something our industrial loaves can't. It lasted weeks without refrigeration, protected by what amounted to its own immune system. This wasn't accidental. Medieval peasants, working without thermometers or microbiology textbooks, engineered a sophisticated food through observation, patience, and an understanding of natural processes we've largely abandoned. The bread that fed Europe's laborers through centuries of backbreaking work wasn't inferior to ours. In nearly every measurable way, it was superior. The foundation of this biological masterpiece began not in the oven, but in the fields. Medieval peasants didn't grow the pristine, high-gluten wheat that fills modern bakeries. They couldn't afford that luxury. Most peasant flour came from maslin, a deliberate mixture of wheat and rye sown and harvested together as a single crop. This wasn't ignorance, it was sophisticated risk management. Rye thrives in poor soil and cold weather where wheat fails. When drought struck or frost came early, the rye survived. If conditions favored wheat, that crop flourished. By growing both together, peasants built an insurance policy directly into their fields, ensuring there would always be grain for flour when harvest came. But maslin was just the beginning. Depending on region and harvest quality, peasant flour incorporated barley, oats, and in lean years, even ground peas or beans. We might call this adulteration. They called it survival. What we've forgotten is that this forced diversity created a far more complete nutritional profile than any single grain could provide. Each addition brought different proteins, fibers, and mineral complexes unavailable in pure wheat. The true transformation happened at the mill. Whether ground by hand with stone querns or at the Lord's watermill, the process was slow and cool, never heating the grain enough to destroy its living nutrients. Most importantly, medieval milling ground the entire kernel, the starchy white endosperm, the fiber-rich outer bran, and the oil and vitamin-packed germ at the core. Modern white flour is just that starchy center, stripped of everything else. Peasant flour was whole and complete. The bran provided the fiber that would slow digestion and feed beneficial gut bacteria. The germ delivered B vitamins, healthy fats, iron, and magnesium. This coarse, dark flour that we'd consider inferior was actually nutritionally superior in every way that mattered for human health. Before a single loaf was baked, before fermentation even began, the flour itself was already a more powerful food than anything produced by industrial roller mills. The foundation was set. Now it needed life. In a world without commercial yeast packets, how did peasants make bread rise? They captured something invisible, something alive in the air around them, and cultivated it into the most valuable possession in their household, the perpetual leaven. This was microbiology without microscopes, a living culture that would be passed down through generations like a family heirloom. The process began simply. Flour mixed with water, left in a wooden bowl, exposed to open air. Within days, wild yeasts, primarily Saccharomyces cerevisiae, the same species used in modern baking, would colonize the mixture. These microorganisms existed everywhere, floating in the air, clinging to grain kernels, living on the baker's hands and wooden tools. But yeast alone wasn't the secret. The real transformation came from the partnership with lactic acid bacteria, or LAB, primarily lactobacillus species that thrived in the same environment. This wasn't a single organism working in isolation. It was a symbiotic culture, a microscopic ecosystem where two different life forms worked together in perfect balance. The wild yeast consumed sugars in the flour and produced carbon dioxide gas, the force that would make dough rise. The LAB consumed different sugars and produced lactic and acetic acids, creating the tangy flavor we associate with sourdough. But these bacteria did something far more important than flavor. They created the bread's nutritional power and its remarkable ability to resist spoilage. Once established, this leaven became a living entity that required care and feeding. Each time bread was made, a portion of dough was held back. This mother dough was fed with fresh flour and water, keeping the culture alive and active. The cycle continued indefinitely. A leaven started by a grandmother could be passed to her daughter, then to her granddaughter, carrying forward a unique microbial signature shaped by local conditions, local grain, and the specific bacteria and yeast strains of that household and region. Some leavens were decades old. The culture adapted and evolved, becoming more stable and reliable with age. This wasn't magic or superstition, it was practical microbiology. Peasants understood through observation what scientists would later confirm in laboratories, that this living culture was reliable, that it improved with maintenance, and that it transformed flour and water into something far greater than the sum of its parts. The leaven was the soul of their bread, and everything that made medieval sourdough superior to modern loaves began here, in this bubbling, sour-smelling mixture of wild microorganisms working in ancient partnership. The leaven was alive. The flour was whole. Now came the transformation that separated medieval bread from everything produced in modern factories. 24 hours of slow, wild fermentation. This wasn't a step in the process, it was the process, a biological metamorphosis that fundamentally restructured the dough at the molecular level, breaking down toxins, unlocking nutrients, and building the bread's natural defenses against decay. Modern commercial bread is rushed through production in 2 to 3 hours using concentrated baker's yeast. Medieval dough sat for an entire day, sometimes longer, while wild yeast and lactic acid bacteria slowly worked through every particle of flour. During this extended fermentation, the dough wasn't simply rising. It was being chemically and nutritionally transformed into a different substance entirely. The first transformation targeted what nutritionists call anti-nutrients, compounds in whole grains that actually prevent your body from absorbing minerals. The most significant of these is phytic acid, a molecule that binds tightly to iron, zinc, calcium, and magnesium, making them biologically unavailable. Modern whole wheat bread, baked quickly without proper fermentation, delivers these minerals but locks them away where your digestive system can't access them. The long fermentation of medieval sourdough activated enzymes called phytases, naturally present in the grain, while the acidic environment created by the LAB accelerated the breakdown of phytic acid. After 24 hours, nearly all of it was neutralized. The bread didn't just contain minerals, it released them. A peasant eating this bread absorbed dramatically more nutrition from the same grain than we do from unfermented whole wheat products. The second transformation was pre-digestion. The enzymes activated during fermentation began breaking down the complex carbohydrates and proteins in the flour, including gluten. The bacteria and yeast essentially performed the first stage of digestion before the bread ever reached someone's stomach. This made the finished loaf remarkably easy on the digestive system, delivering energy without the bloating, inflammation, or blood sugar spikes that accompany modern bread. The grain was already partially broken down into simpler, more accessible forms. The third transformation was preservation. As LAB consumed sugars, they produced lactic and acetic acids that lowered the dough's pH, making it increasingly acidic. This acidic environment became the bread's natural immune system. Mold spores and spoilage bacteria that would quickly colonize modern bread cannot survive in this acidity. A finished loaf could sit on a shelf for a week, sometimes 2, without any chemical preservatives, without refrigeration, without even wrapping. The crust would harden, but the interior remained edible and safe. Compare this to a supermarket loaf, loaded with preservatives, that still develops mold within 3 to 4 days. This 24-hour wait wasn't inefficiency or ignorance. It was biological engineering that modern industrial baking has deliberately abandoned in favor of speed and profit. Every hour the dough sat was another hour of chemical transformation, another increment of toxins neutralized, nutrients unlocked, and protective acids accumulated. By the time it entered the oven, medieval dough had become something fundamentally different from the flour and water it started as. it had become alive, defended, and nutritionally optimized. The slow transformation was complete. Now it needed only fire and stone to forge it into its final, enduring form. The transformed dough was ready, but most peasants didn't own an oven. A personal oven was expensive to build and dangerous to operate in timber-framed cottages where a single spark could ignite a roof. Instead, bread baking happened at the communal oven, typically a large wood-fired masonry structure owned by the local lord or shared by the village. Baking day was a social event, with families arriving in sequence to use the shared heat. But this communal system wasn't just about economy. It forced a specific baking method that gave medieval bread its final, crucial characteristic: the armor-crust. These communal ovens were built from brick or stone, designed to absorb and radiate intense heat. A fire was built directly inside the baking chamber and left to burn until the masonry walls glowed with stored thermal energy. Once the structure was fully saturated with heat, the coals and ash were swept out, leaving only the radiant heat trapped in the stone. The oven floor, a thick slab of heat-soaked stone or brick, became the baking surface. The shaped loaves were placed directly onto this scorching stone using a long wooden peel. The moment the wet dough touched that surface, two critical reactions began. First, the intense bottom heat caused an explosive final rise called oven spring. The water in the bottom of the dough instantly converted to steam, expanding rapidly and driving the loaf upward in one last dramatic surge. Second, and more importantly, the combination of high heat and steam initiated the Maillard reaction, a complex chemical process where sugars and proteins in the dough's surface caramelized and browned, creating hundreds of new flavor compounds and forming a thick, dark, almost leathery crust. This crust wasn't a flaw or a sign of overbaking. It was a structural shell, an edible container engineered by heat and chemistry. The exterior caramelized into a barrier that was initially hard, almost woody in texture when fresh. But this armor crust served a precise function. It locked moisture inside. While the exterior hardened into a protective layer, the interior crumb remained soft, dense, and moist. As the bread cooled and aged over the following days, moisture from the interior gradually migrated outward into the crust, softening it slightly while the crumbs stayed preserved. The thick shell prevented the loaf from drying out, maintaining its edibility far longer than any thin-crusted modern bread could survive. This stone baking method created a loaf that was structurally and chemically defended against time. The crust was both armor and seal, a natural packaging system that required no additional technology. When a peasant broke open a 3-day-old loaf, the interior was still yielding and fresh, protected by the dark shell that had formed in those first violent minutes on the stone floor. The bread was forged, not merely baked, and now, finally, it was ready to sustain life. The 700-year-old loaf is complete. Whole grain flour, fermented for 24 hours by wild microbes, baked on stone into an armor-crusted cylinder of dense, dark bread. Now we answer the central question. Why was one thick slice of this peasant food worth 5 slices of modern white bread? The first answer is energy delivery. Medieval Maslin bread, because it was a fermented whole grain product, had an extremely low glycemic index. The complex carbohydrates, slowed further by intact fiber and partially broken down by fermentation, released glucose into the bloodstream gradually over hours. This was fuel designed for sustained physical labor. A peasant eating a thick slice at dawn would feel steady energy through 12 hours of plowing, harvesting, or splitting wood without the crash that follows a sugar spike. 5 slices of modern white bread deliver a massive, rapid surge of glucose, a blood sugar spike that triggers insulin release, followed within an hour by hunger, fatigue, and the need to eat again. The medieval loaf didn't just provide calories, it provided stable, long-burning energy that matched the demands of an agrarian workday. The second answer is nutrient density. Because fermentation had neutralized the phytic acid, the minerals locked inside the whole grain were now bioavailable. Iron for oxygen transport, zinc for immune function, magnesium for muscle and nerve operation, calcium for bone maintenance. These weren't listed on a label. They were chemically freed from the grain itself and ready for absorption. Add to this the B vitamins created as byproducts of bacterial fermentation, the complete proteins preserved from wheat and legume flour, and the healthy fats from the wheat germ that survived cool stone grinding. The bread wasn't a side dish. It was a complete food, often eaten with nothing more than cheese or thin soup, because it delivered nearly everything the body required. Modern white bread, stripped of bran and germ, offers primarily starch and gluten, empty calories that fill the stomach without nourishing the body. The third answer is satiety. The high fiber content and dense crumb of medieval bread created lasting fullness. One slice was genuinely satisfying because it took time to chew, time to digest, and provided bulk that signaled satiety to the gut. Modern bread is engineered for the opposite effect. Soft, quickly consumed, digested rapidly, designed to leave you wanting more. The peasant slice wasn't merely filling, it was satiating at a biological level, reducing the total amount of food required across the day. The fourth answer is digestive health. Though baking killed the live cultures, the fermentation process had already transformed the bread into a gut-friendly food. The pre-digested proteins and carbohydrates reduced digestive strain. The preserved fiber fed beneficial bacteria in the colon. The organic acids created during fermentation helped maintain healthy gut pH. This was bread that worked with the digestive system rather than against it, a stark contrast to highly processed modern products linked to inflammation and microbiome disruption. This single slice, dense, dark, sour, protected by its thick crust, represented the pinnacle of pre-industrial food engineering. It wasn't refined or delicate. It was robust, enduring, and nutritionally optimized for the humans who depended on it. The peasants who baked it understood none of the chemistry or microbiology we've described here. They simply knew, through generations of observation, that this method produced bread that kept them alive, kept them strong, and kept them working. The science was invisible, but the results were undeniable. One slice fueled a day's labor because it was designed, through biological processes refined over centuries, to do exactly that. The medieval peasant's loaf was never a symbol of poverty. It was the product of 7 centuries of empirical optimization, a food system that used observation instead of laboratories, patience instead of additives, and natural microbiology instead of industrial shortcuts. These bakers couldn't explain wild yeast strains or measure lactic acid concentrations, but they didn't need to. They understood what worked. They knew that mixed grains survived bad harvests. They knew that the bubbling leaven their grandmother kept made better bread than anything started fresh. They knew that slow fermentation produced loaves that lasted, that tasted right, that sustained heavy labor without leaving them hungry an hour later. What we've described in this video isn't speculation or romanticism. It's documented food science applied to historical methods. The phytic acid breakdown is measurable. The glycemic response is testable. The antimicrobial properties of organic acids are established. Chemistry. Medieval peasants achieved these results without understanding the mechanisms because the processes themselves were sound, refined through generations of daily practice by people whose survival depended on getting bread right. When modern artisan bakers talk about long fermentation, stone hearth ovens, and whole grain sourdough, they aren't inventing a trend. They're rediscovering a technology that fed entire civilizations more effectively than our industrial system feeds us today. The bread that sustained medieval Europe through plagues, famines, and centuries of backbreaking agricultural labor wasn't primitive. By nearly every nutritional metric that matters, mineral bioavailability, sustained energy release, digestive ease, preservation without chemicals, it outperformed what most of us eat now. This matters beyond historical curiosity. It reveals something we've lost in our pursuit of convenience and shelf-stable uniformity. The understanding that food quality comes from biological processes that require time. You cannot rush fermentation and expect the same nutritional transformation. You cannot remove the bran and germ and expect the same mineral content. You cannot replace wild culture with commercial yeast and expect the same preservation or digestibility. The medieval method was slower and more labor-intensive, but it produced objectively superior results because it worked with natural biological systems rather than trying to circumvent them. The peasant standing at the communal oven, sliding a maslin loaf onto hot stone, was practicing sophisticated biotechnology. The bread that emerged, dark-crusted and dense, represented the successful collaboration between human knowledge and microbial life, between agricultural diversity and fermentation chemistry. That loaf, made from nothing but mixed grain, wild cultures, water, time, and fire, kept people alive and working in conditions we can barely imagine. It did this not despite its simplicity, but because of it.